This is section 1.1, part A, on functions. We'll start with a couple of definitions. A mathematical relation is just a way of defining two variables that depend on one another. We usually think of one of our variables as the input or independent variable. In math, you usually see this as the x. And the second variable is the output or the dependent variable. Again, in math, we often think of this as the y. A relation can be described in a lot of different ways, and we're going to see several of them in the chart that we're going to create. Now, a function is a special kind of relation in which the value of every independent or input variable is associated with only one value of the dependent or output variable. If I have a function, I make the definition that the domain is the set of all possible input values. The range is the set of all possible output values. Let's take a look at a few examples. In the first two examples, what I have are descriptions. If I think about the relationship between a word and the number of syllables it has, I can think of it two different ways. If the independent variable or input is the word, and the output is the number of syllables, for example, I might consider the input variable to be math, which is a one-syllable word, and so the output would be 1. I could do an input of geometry, geometry, 4-syllable word, so the output for my ordered pair would be 4. Notice that in every case, as soon as I have a word, it only has a single value for the number of syllables. Math always has one syllable, never 2 or 3 or 4. Geometry always has 4 syllables. So every input has only one output that goes with it, and I can therefore say that yes, this is a function. What if I think about the process the other way around? What if the independent variable is the number of syllables and the dependent variable is the word? If I now select 1 as my input variable, can you tell me what output I'm thinking of? Well, probably not, because there's a lot of different outputs I could be choosing. I could be thinking of the word math, or I could be thinking of the word egg, or any number of other one-syllable words. So notice that for our input this time, there's not just one output, there's lots of different outputs that go with it. And I have to say that this is not a function. Let's try one more. What if the relationship is between the US president and the year in which he was elected? If my input is the year and the output or dependent variable is the president that was elected, I could, for example, say that in the year 2012, the output would be Obama. Now, of course, in 2008, the output would also have been Obama, but that's okay. For each year, there's only one output. If I back up a little bit further, if I go back to 2004, I have the single output Bush. So I'm going to say yes, this is a function. Every input has just one output. What about the other way around? Well, if I start with the president, for example, Obama, what is his election year? Well, now you don't know what I'm talking about, whether I'm thinking about 2012 or 2008. There's not just one output. There's two possibilities for the input of Obama. And so I have to say that this is not a function. All right, let's get to some examples with numbers. In my next example, I have what's called a mapping diagram. The inputs are in the first box, and I'm going to label that x. So my independent variables are the x values. My outputs are in the second box. So I'm going to label that y. My outputs are the y's. The domain is the list of all possible inputs. which in this case is all the numbers in the first box, 2, 4, 6, and 8. The range is all the possible outputs, or all the numbers in the second box, 0, 1, and 2. Let's write down some sample ordered pairs. If I tell you I'm thinking of the input 4, you could tell me for sure the output that goes with 4 is 2, because this arrow goes from 4 to 2. If I tell you I'm thinking of the input 6, you know for sure that the output that goes with that is 1. In fact, every input has just one output, and so we're going to say yes, this is a function. When I look at the next example, again, I'll just call the first box x and the second box y. My inputs, or x values, are either 2 or 4, so that's my domain. And my outputs, or y values, could be 0, 1, or 2, so that's my range. If I give you the input 2, you know for sure that the output I'm thinking of is 1. So we're okay so far. But look what happens when I give you the input 4. Now I say, well, wait a minute. The output could be either the 0 or the 2. And so we have a problem. The input 4 has 2 possible outputs. And I have to say no. This is not a function. We'll look next at defining a function, or a relation anyway, using just a set of ordered pairs. In this case, again, we'll think of the inputs as the x values of each ordered pair. And if I pick out all those x values, I can see that they are 1, 2, 3, 4, and 5. The y values would be all of the possible outputs, or second values. And the list there would be the 4, 6, 8, 1, and then the last ordered pair is another 6 for an output. I don't need to list it again, so I'll just leave it there. And I don't really need to list sample ordered pairs because all of the ordered pairs in the list are possibilities, but I'll just pick one out, say 3, 8. And notice that because every first element is different, there's no single input that has 2 possible outputs. Every input's got just one output. And I can say that yes, this is a function. In the next example, if I look at my inputs, or x values, the domain would be 5, 3, and 8. That 3 was already listed, so I don't need to repeat it. The outputs, or y values, my range is 0, 1, 4, and 7. Now this time, I do have a bit of a problem, so when I list my sample ordered pairs, I'm going to list the ones that give me trouble, specifically the 3. If I tell you the input is 3, the output could be 1, but actually the output could also be 7. So for the single input 3, I have 2 possible outputs, meaning this is not a function. Another way to look at relations is by looking at a graph. When I look at my graph, the input, or the x values, could actually be anything, although in this particular case I can only see the parts from x equals -3 to x equals +3. So if we assume this doesn't go any further and we assume this function ends right here, I'm going to say that my domain would be all the numbers between -3 and +3. And notice what I'm using here is called interval notation. The brackets mean include the -3 and the +3, and also include everything in between them, all the fractions, all the decimals, everything, for that interval notation. The y values go from a lowest y value down here at -1 to a highest y value at the top of +3. So in interval notation, I could list my range as going from -1 to +3, including all the numbers in between. Now, is this a function? Well, one way to tell is to pick an x value. Let's say 2. And when x is 2, I can see that the y value has to be 1. If I picked another x value, say -1, I can see the y value here is maybe about -1/2. In fact, every x value has only got one y value associated with it. And sometimes we use what we call the vertical line test to determine this. If you draw a vertical line anywhere on the graph, it only intersects the graph in one spot. What you're really doing with that vertical line is defining an x value, like x equals 2 here, and saying when x is 2, there's only one place on the graph, one y value that goes with it. So if I want to list a couple of ordered pairs, we had found the ordered pair 2, 1. And we had seen that, well, let's use one that's nice and easy. Say 0, -1 is another good point. Every x has only one y. Yes, this is a function. And furthermore, I can say it passes the vertical line test. All right, when you look at the next example, we can see right away if we're thinking about that vertical line test that we're going to have a problem. Certainly if I were to draw a vertical line on that graph, it's very quick to see that we do intersect the graph in 2 different places, not just one. So already I know this is not going to be a function. Let's run through the exercise here. If I once again think of my function as stopping, or my relation as stopping at those points, the x values run from a smallest value here at -2 to a largest value at 3. So my domain would go from -2 to 3. The range, or the y values, go from a smallest value, well, I'm going to have to estimate there, maybe it's about -2.2 to +2.2. Okay. I've seen that when x is 2, y could either be +2 or y could be -2. And because the same input has 2 different outputs, I have to say that no, this is not a function. In fact, it fails the vertical line test. The last way that we might have a relation defined is using an equation. And unless someone tells you differently, the default would be to once again consider the x the independent variable and the y the dependent variable. When I look at an equation like x plus y squared equals 9, I could find sample ordered pairs just by selecting a value of x and calculating the value of y that goes with it. So for example, I'll pick an easy one. If I pick x equals 0, my equation becomes 0 plus y squared equals 9. But what number, when you square it, equals 9? Well, certainly 3 does, but is there another number whose square is 9? Yeah, -3 is also a possible solution to that equation. So notice that for my input 0, I got an output of 3, but I also got an output of -3. Here again, I have to say this is not a function. I have the same output giving me, or excuse me, the same input giving me 2 different outputs. In the next example, if I do the same thing, if I just pick x equals 0, my equation is 0 squared plus y equals 9, which really just says that y equals 9. So for my input x and my output y, I can say that when x is 0, y is 9. The input 0 just gave me one output, and I could pick some other x's as well, but I can see that a single input does give a single output, so yes, this is a function. If you'd like to practice what we've just learned, I've got a set of practice problems available to you. And if you'd like to try them, all of the solutions to these problems are posted in my math lab so that you can check your work. You may want to pause the video and do that now, and then come back for the rest. The next part of this is to talk about what's called function notation. With function notation, we simply sort of rename our y. Y is usually what we call our dependent variable. But what we're going to do with function notation is call it f of x instead. F becomes the name of our function. Sometimes it's f, it might be g or h or any other letter, but it names our function. And the x, or what we call the argument, specifies what variable is the input variable. So when I write f of x, I'm telling you my function is named f, and my input variable is going to be x. Now my function is 2x plus 5, and notice that the argument x is definitely got to be the variable that's used in the function itself. Okay. Since f of x and y both occupy the same position in these equations, they're interchangeable. And sometimes we even write y equals f of x equals 2x plus 5. Notice the vocabulary that I'm using here. In this notation, the f of x is read exactly that way, f of x. It's not f times x. And I know a lot of times in algebra we use parentheses to signify multiplication, but in this case the notation is not a multiplication. It's simply a function of an input variable. Let's take a look at a few examples. For each of these problems, we're going to assume that f of x equals 2x plus 5, and g of n equals n squared minus 2n minus 4. Notice that with g, I gave the function the name g, the input variable is n, and the expression that I gave you did indeed include n's as the variable. If I first ask you to find f of negative 3, I know that I'm looking at the function f, so I start by focusing on the first equation. Now negative 3 is in place of the x, so I'm going to replace the x in the expression with a negative 3. That gives me negative 6 plus 5, or negative 1. So f of negative 3 is negative 1. Notice that what this is really telling me is that when x is negative 3, y is negative 1. Let's try that again. I want to do g of 5. I'm going to go to the g equation this time, and I'm going to replace the n's with 5's. So I would have 5 squared minus 2 times 5 minus 4. Doing the arithmetic, 25 minus 10 minus 4 gives me 11 for the function value. And again, what that's really telling me is when x equals 5, y equals 11. We can do arithmetic with our function values as well. In the next example, I'm asking you to take 4 times f of 1. So the multiplier of 4 I'm just going to leave out here first. And then I'm going to calculate f of 1 by substituting 1 for the x in the function f. 2 times 1 plus 5. Doing my arithmetic, that would be 4 times 7, or 28. Example 4. I want to take g of 8 divided by 8. So once again, I'm going to leave that 8 in the denominator for now. And I'm going to calculate g of 8 first. Plugging 8 in for n, 8 squared minus 2 times 8 minus 4. That would be 64 minus 20 would be 44. Divided by 8 comes out to 5.5. So arithmetic can be done with function values. Just make sure you calculate the function value first and then perform whatever arithmetic you need to perform on it. Here's a couple more examples. Sometimes we need to plug not just numbers but expressions into our functions. So if I asked you to find g of z, all I'm really telling you to do here is to replace the n's with z's. So I would simply get z squared Sorry, I had a little bit of a glitch there. When I'm trying to replace the n with a z, I would just get z squared minus 2z minus 4. Sometimes it's more than just a variable for a variable swap. In the next example, f of 4w minus 1, I'm going to replace the x with the whole expression 4w minus 1. Parentheses are really important here. So notice how I'm going to say it's 2 times, and then using my parentheses, 4x minus 1 plus 5. I'll use a distributive law, 8x minus 2 plus 5, and then just simplify that to 8x plus 3. In number 7, I want to take g of n plus 3. So I'm going to replace the n's in the g function with n plus 3's. So first of all, I'm going to get n plus 3 squared. And then I'm going to subtract 2 times n plus 3 minus 4. Notice each place I had an n, I've now replaced it with an n plus 3. This is going to take a little bit of algebra. Remember that to do n plus 3 squared, you actually have to do FOIL. It's n plus 3 times n plus 3, which is n squared plus 3n plus 3n plus 9. And then distributing the negative 2, minus 2n minus 6, and then minus 4. We'll combine our like terms, n squared plus 4n and plus 5. Try one more like that. This time I want to do g of x cubed. So I'm going to replace the n's in the g expression with x cubeds instead. So I would have x cubed squared minus 2 times x cubed minus 4. Once again, notice that where there used to be n's, I now have x cubeds instead. Remember your laws of exponents from beginning algebra? When I have power raised to a power, I multiply my exponents. So x to the 6th minus 2x cubed minus 4. We'll try this again with a couple of new functions. This time h of x is equal to the opposite of x plus 7, and k of t is equal to t cubed. I'd like to find x this time. Find x if h of x equals 10. Notice I'm giving you the opposite type of information. I was before giving you the x value and asking you to find the outputs. Now I'm giving you the output and asking for the inputs. So if h of x is equal to 10, I'm going to replace the h of x itself with a 10. And then I'm going to solve the resulting equation. If I subtract 7, 3 is equal to the opposite of x, and then I'll divide by negative 1. So x is negative 3. We'll try that a couple more times. This time I want to find t if k of t equals 8. So I'm going to replace the k of t with the 8 and solve the resulting equation. If 8 is equal to t cubed, then t must be equal to 2. Number 3, we're supposed to find t if k of t equals negative 1,000. So if I have negative 1,000 equals t cubed, then t would be the cubed root of negative 1,000. And you may know that that's negative 10. If not, of course, you can always use your calculator to find that value. All right, one more example like this. Find x if h of x equals negative 15. So I replace the h of x with negative 15. And solve for x. We'll subtract the 7. So negative 22 is equal to the opposite of x. And then divide by negative 1. So x is 22. The last portion of this video is devoted to the arithmetic of functions. We can actually add, subtract, multiply, or divide functions using our normal rules of algebra. We're given 3 functions for these examples: f of x, g of x, and h of x. And if I'm being asked to find in example 1 the function g plus h of x, I'm literally going to add g, which is 5x minus 4, plus h, which is x squared minus 6x. Because of the addition, I can really just ignore the parentheses and combine like terms. I would have x squared minus 1x, or just minus x, minus 4. And that single function is actually the sum function of g plus h. Now, if I wanted to know what is g plus h of negative 1, all I need to do is plug the negative 1 into the function that I just found. So I would have negative 1 squared, subtract negative 1, minus 4. 1 plus 1 minus 4 gives me negative 2. Let's try this with the other operations. H minus f of x. I take my h function, x squared minus 6x, and subtract the f function, which is 3x squared. Combining some like terms here would give me negative 2x squared minus 6x. And that's the difference function, h minus f. If I now want to know what is h minus f of negative 3, I'm going to plug the negative 3 in for x. Which gives me negative 2 times 9 plus 18. Negative 18 plus 18 is just going to give me a 0. By the way, notice that when the number follows the function, right, it was h minus f of negative 3, the negative 3 replaces the variable, and we do the calculation. Earlier, we were looking at numbers in front of the functions, in which case they were just multipliers. So there is a difference. All right, what about multiplication? Well, if we want to multiply f times h of x, we're going to take our f function. Oops, and I've forgotten what that was. Hold on just a second. Sorry about that. We take our f function, which was 3x squared, and we multiply by the h function, which is x squared minus 6x. This is simply a distributive law multiplication, so we'll do that. 3x to the 4th, notice we're adding those powers again, minus 18x to the 3rd, adding second power and first power, and that's the product function. In number 6, I want to find f times h of 2. Because the 2 is after the function, it's telling me to replace the variable with 2. So I'd have 3 times 2 to the 4th minus 18 times 2 cubed, which would be 3 times 16 minus 18 times 8. And plugging that into my calculator, I get negative 96. All right, last operation. We have division, g divided by f of x. Our g function was 5x minus 4 divided by the f function, which is 3x squared. There's really not much I can do to simplify that, so I'm simply going to leave that as my quotient function. And in number 8, I'm now being asked to plug 0 in for x. So I have 5 times 0 minus 4 divided by 3 times 0 squared, which is negative 4 divided by 0. And remember that division by 0 is undefined, so there's no real answer to this problem. If you'd like to practice some of this function notation and function arithmetic, I recommend that you try the next set of practice problems. Once again, remember the solutions are posted in my math lab so that you can check your work.